This conference will now be recorded.
Hello everyone, last day we have started miscellaneous reaction, and under this category the first reaction is Cannizzaro reaction that is started, but the intermolecular version we will see now. Some more miscellaneous reactions will be discussed and also related problems. Intramolecular, when we are saying, that means two carbonyl groups that are required in Cannizzaro reaction, both will be present in the same molecule. So here we have taken this example, PH, then CO, then CHO. That means we have carbonyl carbon and we also have aldehyde carbon. Now among these two carbonyl, the second one is more electrophilic in nature. Okay, because it is aldehyde carbon. So that is why HO minus it will attack here. Another reason is also that you can think that why not the other CO is not so nucleophile. It is because it is directly attached to pH ring. Now in pH ring, when it is attached, resonance with the double bonds of pH ring is possible. That means this type of resonance structure we can have. There is positive charge, CO negative. Now because of this type of resonance, the double bond character of carbonyl group that is decreased, and this is the reason why this carbon is less electrophilic, and the other one, that is the CO, which is just beside it, that is more electrophilic, because in this carbonyl group this type of resonance with CC double bond is not possible. Here the HO minus ion, which is coming from the base, that is attacking here, which is the nucleophilic attack, and after that there will be negative charge over oxygen. And we know that after this first step, what happens next? The hydrogen which is attached to this carbon, where the nucleophile is attacking, this hydrogen will be removed. That means this carbon hydrogen bond will be broken, and this hydrogen will be removed in the form of hydride. So this OH, if we consider as if this is, that is the oxygen hydrogen bond is broken, there is a C double bond O, and carbon hydrogen bond is breaking, and negative charge over the other carbonyl carbon. So now there will be C double bond O, C, and O minus, that is already present, and this H now it will attach to this oxygen because there is negative charge. So directly now you can write COO minus and OH, but we know that there will be, actually there is proton exchange, because this H and the other H, if we consider, obviously this is the alcoholic part. We know when there is Cannizzaro reaction between two individual molecules, what we get? We get alcohol and we get carboxylate salt, that is RCO2 minus. But in this case, both are part of the same molecule. Fine. So here you can see the carboxylate ion is present, COO minus, and this is the alcohol part, and this is the RCOO minus part, this part. But they will be remaining in the same molecule. This is because it is intramolecular reaction. And if we protonate it, that is, the medium is basic, but if we protonate it, there will be formation of ultimately neutral compound OH and COOH. So this is actually as if alpha hydroxy carboxylic acid, because with respect to this carbon, this position is alpha, and alpha position there is OH group, so it is alpha hydroxy carboxylic acid. One more example we will see. Here we have two CHO group present in the ortho position of the benzene ring. Alkali we are using, suppose it is NaOH solution. So the nucleophile HO minus, if we write the molecule COH, now HO minus is attacking any one of these CO because both are symmetrical. There will be negative charge. So what structure we will get? Benzene ring is not disturbed, O minus, OH, and there is already one H, COH. Okay. Now this O minus, if it is making C double bond O, this H will be removed, and ultimately it will attack this carbon. So what we will get? COOH, right? O minus H, but here proton exchange will take place, that is minus H plus and then plus H plus, because as the medium is basic, so obviously the CO2H group that will remain in the form of carboxylate R. So this H now it will be attached to O minus. So ultimately it will be CH2OH. Okay. But finally, as there is H2O plus, so what you will get? You will get this molecule that is already shown in the picture. CO2H, CH2OH in the same molecule, that is in benzene ring at 1 and 2 position. That is ortho position. Fine. Now, one important thing in this reaction you have to remember, as here the two CHO group, they are ortho to each other. So that is the reason this type of hydride shift, it is possible. That is hydride that is shifting towards, it is removed in the form of H minus, and that is also attacking another CO group. So this CO group, normally if it is not intermolecular, it is separate molecule. So it has to attack another molecule. But here it is very close at ortho position. Suppose if you take same molecule but the two CHO group they are not at ortho in meta, then it will be very far from it, and the probability of reaction will be less. As it is at ortho position, it is very close to, that is the two groups are close to each other. So at that is attacked by this H minus towards this CO, that is facile process. How many compounds? As you are seeing here, total 6 compounds are given. There are aldehyde group and also keto group in some molecules. How many of them will give Cannizzaro reaction? Options are 2, 3, 4, 5. Now the condition to give Cannizzaro molecule or ketone molecule with no alpha hydrogen, then only Cannizzaro reaction is possible. So basically in these 6 molecules, you have to check in which case alpha hydrogen is present. If it is present, Cannizzaro not possible. Look at the first molecule, it is formaldehyde. In this molecule with respect to CO, there is no alpha carbon, so no question of alpha hydrogen. So this is not the molecule which will not give Cannizzaro. Then the second molecule with respect to CO, you have 2 alpha position. So here aldol reaction will take place. So this will not give Cannizzaro. So this is the molecule which will not give Cannizzaro. So we will not count it because we have to count those molecules which will give positive test. Next molecule, furan ring, CHO group is attached. Now here with respect to this C double bond O at alpha position, which is this one, there is no hydrogen. So this will also give Cannizzaro. Number 4, if you see there are 2 CHO group, that means 2 aldehyde. You can also write the same molecule in this way so that you can easily understand. Now with respect to this CO, if you consider this carbon alpha, there is hydrogen present, you can say, but this type of hydrogen, it is not enough. Alpha hydrogen, it should be like where carbonyl generation is possible, but here carbonyl generation is not possible in presence of this. So that is why don't consider this hydrogen as alpha hydrogen, right? And that is why this molecule, it will give Cannizzaro. In this case aldol not possible. Then molecule number 5, here with respect to CO, this carbon is alpha and here hydrogen is present. That means it can give aldol CHACO, CH to CH. Okay. And then molecule number 4. Now in molecule number 4, here we have, this is alpha carbon, this is alpha carbon. That means alpha hydrogen present, right? So as alpha hydrogen present, so that is why this will also give aldol reaction because carbonyl generation is possible. Fine. Actually, this molecule here correct. These 2 molecules will not give Cannizzaro. And here one printing mistake is there. Basically, this is the molecule where 3 methyl groups are there. There is no hydrogen actually. Fine. So 2 molecules cannot give Canizaro. Rest of the molecules out of 6 they can give. So total 4 compounds can give Canizaro. So correct option should be this option. Fine. And though I'm saying that this is methyl, but suppose if it is hydrogen, then it is possible. Though it is also true that if you generate carbonyl in this position, that is not very stable because of presence of methyl group. But we cannot totally negate that. I mean to say, we cannot say confirmly that aldol will not take place at all. It will take place, but the amount will be very less. Fine, because this carbonyl is not stable. Next question. Major products of the following reaction. So this reaction, there are 2 aldehyde molecules. In both aldehyde, there is no alpha hydrogen. Here also alpha carbon, no hydrogen, and here we do not have any alpha carbon, so no question of hydrogen. Now these type of molecules, they are suitable for Canizaro. That means we will have Canizaro reaction here, and this is crossed Canizaro because 2 different molecules we have taken, right? We have taken 50% NaOH, then acidification, that is H2O plus, that is acidic condition will be there. Now if we consider the first combination, PHCH2OH, PHCOOH. So this reaction product combination is possible only if 2 molecules of benzaldehyde is reacting. But that is not possible because when ACHO is present, the attack of HO minus, that is the nucleophilic attack, that will obviously take place first to ACHO, because this is the aldehyde which is most reactive, because in ACHO both sides there is hydrogen. There is no alkyl group, and as there is no alkyl group, from electronic point of view, this carbon is highly electropositive, no inductive effect, that is donating effect from both sides. And from steric point of view also, this attack at this center is very suitable because these 2 groups are very small, nucleophile can easily attack. So that is why the first product combination not possible, because this will be the combination of product when you have taken 2 molecules of PHCHO without any ACHO. Then the second one, what is the combination? Here the combination is alcohol. We know that when there is Canizaro, there is 1 alcohol and 1 acid. So reduction, oxidation both take place simultaneously. Now which molecule, that is in cross Canizaro reaction, we have already seen in last class that molecule will give, that is will be oxidized, which is first attacked by HO minus. Okay, so according to that logic, this should not be the correct combination, because here CH3OH, if it is correct, that means ACHO, formaldehyde is reduced and benzaldehyde is oxidized. But if you consider the opposite possibility, that is ACHO is oxidized and PHCHO is reduced, then that is opposite possibility is given in option 3. And if you consider the last option, this product combination is possible only if you have started from 2 molecules of ACH. So this is also not possible. So these 2 are basically normal product. That is individually, if you take 2 molecules PHCHO or 2 molecules of formaldehyde, then only these 2 options are correct. But the middle 2 options, 2 and 3, they are actually crossed Canizaro product. But which one will be correct? It is basically the third one, because we have seen that when there is any of these aldehyde is ACHO, it is always formaldehyde which is oxidized. And that is clear from, if you write the full mechanism, you can easily understand it, because the first attack is towards ACHO, that is the first attack by HO minus. That we have already discussed in detail in the last class, so I am not going into the details. Here ACHO will be oxidized. So formic acid is one product. Another product is reduction of PHCHO, which is benzyl alcohol, PHCH2OH. The compound A in the following reaction. Compound A, starting material, you are treating it with CH3MgBr and H2O. So we know in Grignard reaction, first there is attack by the Grignard reagent. In this case, Grignard reagent is MEmgBr, and then it is to be hydrolyzed by water. Because the OMgBr bond, we break it to OH. That is why water is needed. Now the second step, there is concentrated H2SO4 and heat. So this reagent combination and heat, we use it when we want to do dehydration. So it may be that first, that is attacked by CH3MgBr when occurring to A. If A is having any carbonyl group, then you are getting alcohol. And this alcohol, when you are treating with the concentrated H2SO4, there will be dehydration. So we should get some CC double bond. There must be some CC double bond in B, and that is again confirmed by, look at the reagent O3ZnH2O. So this reagent combination we use in ozonolysis reaction. First there is treatment with O3, ozone gas. Second is reducing agent, Zn and H2. Fine. So ozonolysis can occur only if there is CC double bond. That means B must contain CC double bond. So in C there should be one carbonyl group. In D also there should be another carbonyl. Now individually, if you have taken C, you are treating it with concentrated KOH and then heat. What you are getting? You are getting potassium salt of benzoic acid and PHCH2OH. Now this product combination you can get only if you have started from two molecules of PHCHO. Then only you can get these type of two products, carboxylate and alcohol, which is Canizaro product. So two same molecules of aldehyde you have taken and you are getting salt and CH2H. Because why salt? Because you have not used any H plus in the last step. So this must be, C must be PHCHO. And D, when you are treating it with BaOH whole 2, barium hydroxide, which is also basically source of HO minus, you are getting this molecule. Now this molecule, see, it is alpha beta unsaturated carbonyl compound with respect to carbonyl group. Alpha and beta position, there is unsaturation, so it is alpha beta unsaturated carbonyl. And remember, in aldol reaction, the first product is beta hydroxycarbonyl. And after that, when you do the dehydration in the second step, then we get alpha beta unsaturated carbonyl. So this must be aldol product. Basically, it is aldol condensation product. So what should be D? D should be acetone. So D is CH3COCH3. If you break at this portion from left hand side, it is one CH3 COCH3, from right hand side another CH3 COCH3, and C is PHCHO. Now if I write D and C in this way, PH C double bond OH, that is I am writing the two carbonyl as if they are facing each other, so that you can understand how alkene is obtained. So retro if you do, it will be, that is the alkene B is something like this. Sorry, it is B. Okay. Now B you can get, you are getting by dehydration. That means if you imagine the previous step, there must be one OH and H from which you are getting this dehydration. Now two possibilities may be there. One possibility is if it is like this, that is H and OH, if their positions are like this. Another possibility is if, see, this is also possible, right? So these two are possible product when A is treated with CH3MgBr. Now among these two, how you will understand which one is basically correct? Now this product, suppose it is 1, this is 2. So 2 you can get, how? You are treating CH3MgBr, right? Treating this molecule CH3MgBr. Now if I write the retro step, it will be PH CH2 CHO. So if A is having this type of structure and you are treating it with CH3MgBr Grignard reagent, then this part is the nucleophile. It will be attacked here, and what you will get? PH CH3MgBr. sorry, it is CH3. So if the CH3 is attacking here, then you are getting product number 1. But if you consider this molecule, then see, if you want to do retro, where one of the reaction partner must be CH3MgBr, that you cannot write, because the OH is at this carbon. That means carbonyl should be present at this position. Okay, so it is as if PHCO CHMe2, but that you cannot get by treating it with CH3MgBr. Okay, because if you are adding CH3MgBr, then this carbon should also contain another CH3, but that is not present. It is possible only if you are doing retro with this one. So this is not possible. Okay, so 1 should be the structure of A, not 2. So if it is true, that means this is the correct option, PHCH2CO CH3, right? And you can also count the number of carbons. In D, there are total 3 carbons. Here we have, except PH ring, only 1 carbon. That means in the alkene also 3, 1, total 4 carbon must be there except PH ring. Okay, so that is also present here. And here how many we have? 1, 2, 3, 4. So one of the CH3 is basically coming from CH3MgBr. So in structure A, there should be only 3 carbon, because 4 carbon you are getting only when there is attack by CH3, which is coming from CH3MgBr, right? So correct option will be option 1. Okay, look at the other product combination. If you consider 2 C6H5COCH3, then after the attack of methyl, which is coming from MEMgBr, it will be like this: PHCOH CH3CH3. After that, if you want to do dehydration, concentrated H2SO4 will be used. Then double bond, that is OH, and any of this hydrogen will be removed. So you will get PHCCH3 double bond CH2. And if you are doing ozonolysis on it, D and C type of product you cannot get. So this is not correct. And also look at the carbon number. It is only 2 carbon. And after the attack by CH3MgBr, there will be 3 carbon. But there actually should be 4 carbon, which is clear from the structure of D and C. 3 carbon present in D, in C, except PH ring there is 1. So 4 carbon must be present in the alkene. Okay, so that is why this is not correct. And if you consider this one, PHCO CHCMe2. Now see here, already we have 4 carbon. Now if you are attacking further by another CH3, which will be attacking here, now you will have total 5 carbon. But if according to as we have counted the number of carbon, this is not possible, right? Then this one, if you are attacking Me here, it will be having this type of alcohol structure: CH3, then CH2CH3. And if you are removing this OH and H, there will be double bond at this position. So one molecule, that is after dehydration, the structure should be like this: H, CH3. Okay. Now if you are doing ozonolysis, product combination is CH3CHO and PHCOCH3, but that is not the structure of D and C. So that is why all these options are not correct. After finishing Cannizzaro, next under miscellaneous reaction is benzoin condensation. Now as we are saying condensation, so there must be removal of some group, right? Otherwise why we are saying condensation? Now this reaction involves condensation between 2 molecules of benzaldehyde and it forms benzoin in presence of cyanide catalyst. That means in presence of CN- ion, which is coming from NaCN and KCN. Now here we have example PHCHO benzaldehyde. 2 molecules of benzaldehyde we have taken, In presence of catalytic NaCN, this is the actual catalyst. We will also see the mechanism. Two molecules of PHCHO, now they are joined together. Okay, so new CC bond formation is there. So one part is coming as if from one PHCHO, another part is coming from another PHCHO. Now the reason why we are using only Cn minus as catalyst, why not other catalyst? Why we are saying is catalyst first of all? Because see, if you look at the product structure, there is no presence of Cn minus. That means it is just helping in the reaction. It is not that ultimately it is also present in the product. No, it is not present. It is just assisting in the reaction. That is why it is catalyst. Now the reason that why we use this catalyst, it is a good nucleophile. Okay, then it can stabilize the intermediate ion. We will also see the structure, and also it is excellent leaving group. Now excellent leaving group, this property is very important because ultimately it has to leave the molecule. It is not finally present in the molecule. So if it is having good leaving capacity, it will be better. So now we see the mechanism. So we have started from PHCHO. There is attack by Cn minus. So when the attack by Cn minus, which is basically nucleophile, there is negative charge over oxygen. Now as there is presence of water, then O minus will be protonated in presence of H2O. Now in the reverse arrow, there is presence of HO minus because ultimately there is removal of HO minus. If it is taking proton from water, that means HO minus is removed. Now the next step, these OH, HCN, these three are present. Now HO minus, it is taking this H. So there will be negative charge over carbon. So this is carbanion. Fine. Now this carbanion will attack second molecule. This is the first molecule. This is the second molecule. Now when it is attacking here, there is CC, new CC bond formation. So this is the new CC bond and negative charge is present over oxygen. So see how these two molecules are ultimately attached together. Fine. So here as if when it is attacking here O minus, then this H, now it is changing its position, it is going to this one. Fine, that is within the molecule there is exchange of proton, and finally there will be O minus. This O minus, as if this negative charge, if it is again making C double bond, and in this step the CCN bond is broken and CN is leaving. Now look at the arrow. This arrow is longer. That means in the last step, it is more probable that it will remain in the product side because CN is very good leaving group. So it will try to remain towards this structure, not in this form. And that is possible only because Cn minus is good leaving group. And also now you can understand why this H is changing its position. Because if the H, it is not changing its position, there is no presence of negative charge over this oxygen. And if there is no negative charge, then this type of pushing of electron, as this negative charge is pushed, that is why this Cn is removed so easily. So here negative charge is very important, and that you can get only if this H is shifting its position. Fine. So ultimately we are getting new CC bond. Though here that is, if we look at the overall reaction, it is not that condensation. When we say condensation, we say when there is a small molecule is removed, though that is not directly present, but still you can see as if this H is removed and two molecules are joined together. So that is, it is condensation. But don't don't have to focus so much on this term because it is used mostly, it is written in this way, but you can also see it is benzoin reaction. So whatever it is, but mechanism is like this. Fine. And so this is the first aldehyde, this is the second aldehyde. Mostly when we say why we are saying it benzoin condensation, because this is the structure of actually the benzoin. And as this, whenever we talk about this reaction, mostly the example is given with PHCHO, and the product that you are getting from PHCHO, that is actually benzoin. It is as if alpha hydroxy keto, because with respect to keto group, this is alpha position, alpha position there is OH group, so alpha hydroxy ketone. And why we are saying benzoin? Because it is obtained from benzaldehyde. If you are taking some benzaldehyde derivative, suppose this is not simple benzene ring, there is some substituent. In that case, the product that you are getting, you can say that that is benzoin derivative, not exact benzoin, because this is benzoin, where you have started from two molecules of PH, CHO. Fine. Next reaction is Claisen-Smith reaction. Now remember, in crossed aldol condensation, what we have seen? Crossed aldol means two different carbonyl compounds we have taken with alpha hydrogen, and in that case we have seen that different product combinations possible, because which aldehyde molecule or ketone molecule there is generation of carbonyl, depending on that product, final product may be different. So this reaction is not very efficient in the sense that it can produce different potential product. But if there is so many mixture of products, purification of them is really difficult. Now, one way to limit the formation of so many different aldol products, one solution we can find out, and that solution is actually this reaction. So what we can do is to make sure that one of the carbonyl compound that is used, suppose you are using A plus B, both are carbonyl compound. So one of these carbonyl compound, there should not be any alpha hydrogen. So if it is so, suppose in A there is no alpha hydrogen, that means carbonyl will be generated only in B, right? In A you cannot generate carbonyl. So that is the solution, or you can say one way to limit the formation of mixture of products. So in this reaction, again we will take two carbonyl compound, but in one carbonyl compound there will be no alpha hydrogen. So this condensation reaction is an organic reaction in which a ketone or aldehyde holding an alpha hydrogen, that means one molecule will have alpha hydrogen. Another molecule is aromatic carbonyl compound. Now we know in aromatic carbonyl compound alpha hydrogen not possible, right? So that is why here you will not get variety of product. Fine, it will be limited. So general, if we see general scheme, it is A. Suppose this is A. This is A because it has no alpha hydrogen. It is the aromatic carbonyl compound, and it is B. Now in B there is alpha hydrogen. These two are alpha hydrogen. Carbonyl generation is possible. So first there will be carbonyl generation. Look, this reaction condition is just like aldol. So this carbonyl, it will react, that is, it will attack this carbonyl carbon, and as a result we are getting this new CC bond. Here the final condensation product. Remember what happens in aldol? First there is attack by nucleophile, you are getting addition product. After that, when you are heating it, here heat sign is given, then water molecule is removed, one H and one OH, net removal of water. As a result you are getting CC bond, but actually this is the junction point. So this part is basically B and the other part is A. Now actual example, if we see, here we have taken acetone. So acetone is basically molecule B, which is having alpha hydrogen, and benzaldehyde there is no alpha hydrogen. And see here, both side you can generate negative charge, you can generate carbonyl, that means both side two times reaction possible. So that is why one molecule acetone reacting with two molecules of benzaldehyde, so both side reaction is occurring. So ultimately you are getting alpha beta unsaturated carbonyl, but it is both side. Fine. So this is as if extra version of crossed aldol, not normal aldol, because you have taken two different carbonyl compounds, right? So this is also aldol, but it is also known by this name, Claisen-Smith. Number 4, Nove-nasal reaction. Here we have taken one carbonyl compound, which is R1COR2, okay, and Second molecule, it is very interesting. See, there is methylene group. Methylene group is CH2 group. Now both sides there is Z1 and Z2. Now this Z1 and Z2, it may be CO2R, that is ester. It may be C double bond OR. It may be cyano, aldehyde, NO2, this type of group. Now if we look at all these group, one thing is common, all of them are electron withdrawing group. Now you have to take electron withdrawing group, because only if you take this type of groups, that is Z1 and Z2, they must be like this. Then only these two hydrogens will be acidic in nature, because when there is electron withdrawing group and negative charge, if it is obtained by breaking this hydrogen carbon bond, that negative charge will be very stabilized because of this Z1 and Z2. So that is the purpose why we have taken this type of molecule. So this reaction, you can say it is condensation, because finally as if it is removal of this oxygen and these two hydrogen, and there will be CC bond formation. So this part is coming from acetone, sorry, I mean to say R1CR2. Another part is coming from the second reaction part. So this is condensation, because ultimately it is, if you just forget about the mechanism, look at the product side, look at the reactant side. As if O and 2H are removed, that means net removal of water. If we see overall change, now why it is active methylene compound? Because this methylene group is activated. These two hydrogens are acidic in nature. That is why we are calling it so. And two nucleophilic addition of activated methylene compound to aldehyde or ketone in presence of amine type of base. Now the base that you are using, that is type is amine type. So that is why we are saying amine base. What type of amine base? Pyridine or piperidine. Pyridine having this type of structure. It is just like benzene, but if you remove one of the carbon with nitrogen, it will be like this, pyridine. And piperidine. Piperidine is this one. Cyclohexane ring, but instead of CH2, one position there is NH. So if you use this type of amine as a catalyst, actually you have to use this type of catalyst followed by finally dehydration. So that is why it is condensation. Fine. Now if we look at the mechanism, here we have taken this base which is piperidine, and this is molecule Y, active methylene group compound, CO2Et, CH2, CO2Et. Fine. Now this is the active methylene compound in presence of this base, carbon hydrogen bond broken, there is negative charge, that is carbon. Now this carbon it is attacking CH3CHO. This is CH3CHO, negative charge over oxygen. Now in the first step, as this H is taken by piperidine, so piperidine is now positively charged. Now one of these hydrogen can be attached to O minus. So what we are getting? We are getting OH. And up to this, that is, if you look at this molecule, this is the addition product. But it is not final product, because finally there is removal of water. So what we are doing, this OH and this H is removed, as if piperidine is taking this H, carbon hydrogen bond broken, new CC bond is generated here, and carbon OH bond is broken. So ultimately we are getting CC double bond. Fine. So this part is coming from active methylene group, which is Y, and this is actually X. CH3CHO, that is X. So this is Y, this is X. Finally, we are getting CC double bond, and if you consider this carbonyl group, if I write elaborately CO, then CC double bond, and this side there is another COOT. So you can say this is also one type of alpha beta unsaturated carbon, right? So Noble-Nassau reaction, that is also as if a variant of aldol reaction, because in aldol also we first generate carbonon, though here the carbonon that you are generating, it may be different types of structure. It is not restricted to only aldehyde or uh, ketone, fine. It may be ester, it may be, if it is COR, it is obviously ketone. If it is C, it may be CN also, it may be NO2 also. So it is not restricted to only aldehyde or ketone. That is why it is more versatile compared to aldol. But it is a variant of aldol because the mechanism there is similarity. It is widely used in organic chemistry for formation of CC double bond. And the activated methylene group should be of the form like this that we have already seen, where Z is electron withdrawing group. So that is why this type of groups are taken. If you are taking any alkyl group, suppose you are taking R CH2R, where R is alkyl group, no, that will not serve the purpose. This group must be electron withdrawing. No alkyl group. If alkyl group is there, it is not possible. Now some examples if we see of this Noble-Nassau reaction. Here we have taken this benzaldehyde, which is aldehyde, and see, this is molecule X. Remember, X is that reaction partner which is basically aldehyde or ketone. But another reaction partner is Y, which is active methylene compound containing active methylene. So this is active methylene CH2. This side as if it is Z1, another side Z1 and Z2 are same actually. So this CH2 is very acidic hydrogen because of this 2 electron withdrawing group. So what you have to do, just remove this OH and these 2 hydrogens. So this carbon and the active methylene carbon will be joined. So this part is coming from X and the other part is coming from Y. Next we have taken again benzaldehyde, but now we have taken malonic acid. See, this is Z1, this is Z2, both are same. So here it is directly shown by this box as if it is net removal of O and H. If you are not writing full mechanism each time, then it is, there will be generation of C double bond O. And as there is a CO2H group in the same carbon, so further one step extra is possible. Normally up to this is the Noble-Nassau condensation product. Further it is not under Noble-Nassau, but as it is having a special type of structure where same carbon is containing 2 carboxylic acid, and for this type of dicarboxylic acid, if you are heating it, decarboxylation is possible. That means one of the CO2H, there will be removal of CO2 minus CO2. So ultimately you are getting pH CC double bond then CO2H, which is nothing but cinnamic acid. And it is also alpha beta unsaturated carboxylic acid, because with respect to carbonyl carbon of carboxylic acid, we have CC double bond at alpha and beta position. So that is, it is alpha beta unsaturated carboxylic acid, and particularly this molecule, it is having name cinnamic acid. Next we have taken salicylaldehyde, because it is not simple benzaldehyde. OH group is present at ortho position, name is salicylaldehyde. So here what happens, first there is, this is active methylene, so as if removal of H2 and O. So the first structure should be CH double bond C CO2 ET, and as there is OH. So another CO2 ET I am writing in this way. Now if you remove this, that is how it occurs actually. So up to this it is condensation product, the reaction that we had discussed. But this here, as OH group is present at ortho position, so further one step is also possible, which is if this lone pair is attacking here, this carbon oxygen bond broken, OH is very good living group, it will be removed. So finally there is OC bond formation. So this H is removed, this OH is removed, as if it is removal of ETOH. So you are getting now this carbon oxygen bond. Okay, so one of the CO2 group, it is reacting with OH, and it is possible only it is at ortho position. Otherwise, if it is meta position, it will be far from it, reaction is not possible. That is, OH group cannot attack if OH is present at meta or beta. Only possible in octo. Fine. So we are getting here cyclic ring formation. Okay. So remember, up to this it is novenasal condensation, but you also have to check whether further any reaction is possible. So same thing you have also seen in the previous example, where up to this position it is the reaction that we are discussing, but further reaction is also possible. Okay. Actually, this structure, if I write, suppose I am not focusing on this part, I am focusing only on this part. COOH. So with respect to this CO2H, if you see, this is alpha with respect to carbonyl carbon of CO2H. This is beta. So as if it is beta keto acid, because at beta position there is also keto, that is C double bond. So for beta keto acid, this type of decarboxylation is very facile. Fine. So this is number 4, novenasal. Next is number 5, Parkin. Now in Parkin, this reaction is only for aromatic aldehyde. So one reaction partner is aromatic aldehyde. Suppose this is number 1 reaction partner. Second reaction partner is anhydride. So it is a reaction between, you can say it is Parkin reaction, or you can say it is Parkin condensation, because there is also removal of water. So if you consider this reaction in general way, it is reaction between aromatic aldehyde and aliphatic acid anhydride. So the second reaction partner is anhydride. This is the general structure of anhydride. There is RCH2 group, both side of COO-CO linkage. And you also have to take a base, but not just any base you can take. Here, what type of base should be taken, that is restricted. So here you have to take alkali salt of the corresponding acid. But when we am saying corresponding acid, what I actually mean is the acid from which you have this anhydride. We know anhydride how we get, from 2 molecules of carboxylic acid. So from 2 molecules of carboxylic acid, if you are getting this, then the structure of the acid must be like this. 2 molecules of RCH2COH, if you consider OOC, I'm writing in opposite direction. In this structure, if you remove one OH and H, then only you can get COO-CO linkage, that is anhydride linkage. So this is the corresponding acid from which you are getting the anhydride. Now the base that you have taken, that must be the salt form of this acid, not just any acid. So as you have taken here RCH2CO2H, so the base must be like this, CO2, Na or K. Fine. So this RCH2 group, suppose it is CH3 group, which you are seeing here. That means R is H, then only it is CH3. So if it is the anhydride that you have taken, which is basically known as acetic anhydride, because the corresponding acid is CH3COOH, acetic acid. Now the base that we have taken, same acid, heat sodium salt. So you have to take the base only the alkali metal salt of the corresponding acid. And here final product that you get is cinnamic acid derivative. Now cinnamic acid is basically this molecule, PH, CC double bond, COOH. But when I am saying cinnamic acid derivative, that means there may be any other group, PH may be containing any other group at ortho meta para, or in this position there may be any groups also. That is why I am saying it is cinnamic acid derivative. So this is a general structure reaction scheme that is written. So one part is coming from anhydride, another part is coming from ARCHO, aromatic aldehyde, and rest of the part of anhydride that will be removed in this form, RCH2COOH. Okay. Now generally such type of reaction is only applicable to aromatic aldehyde, not just any aldehyde, and suitable for, useful for preparation of substituted cinnamic acid, because here final product is either cinnamic acid or cinnamic acid you will get if you have started from PHCHO and acetic anhydride. Because if it is PHCHO, that means this air is now pH, and if it is anhydride is CH3CO2, sorry, CH3CO OCO CH3, then this R is basically H, so you are getting cinnamic acid. But in general, if we write, we have to write in this way. Now one example, this example I'm going, because this is we have to discuss. First look at this one, number 1, PHCHO. You have taken these two molecule, aromatic aldehyde, which is nothing, very simple one, which is benzaldehyde, and acetic anhydride as the anhydride. Sodium acetate. So one acetic acid molecule will be removed from, that is one side will be removed in the form of acid, and the other part. So this part is coming from benzaldehyde, and this part is coming from this one, sorry, the anhydride. Okay. So cinnamic acid. Now in the next reaction, this is something interesting, because here if we consider, now instead of taking benzaldehyde, what we have taken? We have taken sodium salt of salicylaldehyde. Salicylaldehyde is OH and CHO at ortho position. Acetic acid same. So first there will be formation of compound like this. Sodium salt, so I am writing O minus, CO, then CC double bond, then COOH. So this is actually the Parkin reaction product, but as there is O minus, so further reaction is possible. This O minus, if it is attacking this carbonyl carbon, OH will be removed. As if it is net removal of water, so OC bond is formed. So this molecule is coumarin. Now remember, same type of molecule we have also seen in the previous, that is in case of novenazole, but this is also coumarin type of structure. So, but it is not exactly coumarin. It is, there is UTT group also. So you can say it is coumarin derivative. And in this case, the molecule that you are seeing, this is actual coumarin structure. Fine. So this is not actually, I'm not saying this Parkin reaction product, but as OH group is present, this is nothing but OH group. It is just in salt, sodium salt form, because in that case better reaction is possible. Because if it is in OH form, oxygen will attack through lone pair, but if it is in sodium salt form, oxygen will attack through negative charge, which is more nucleophilic. So that is why it is in sodium salt form, and finally we are getting coumarin. But you will end up with cinnamic acids type of structure if there is no OH group. Try to understand difference. In example number 1, there is no OH group at this position, that is at ortho position, no OH group. But in the second case, there is OH group. So that is why this is not the end product. Further reaction is also possible because there is OH group. Okay. So this carbon and this oxygen will be attached, and you are getting a 6 new ring formation is there. Now this mechanism for this reaction, it is that is complex. So we will see one by one all the steps. Mechanism of Parkin reaction. So this is acetic anhydride molecule. We have used sodium acetate, that means acetate ion is there. Now OAC, what is OAC? OAC is nothing but this molecule. It is written in short form. This is OAC. Okay. So this is attacking H. There is CC double bond formation, negative charge over oxygen. And another reaction partner is ARCHO, aromatic aldehyde. Now this is enolate. Enolate ion formation, first step. Now the negative charge over oxygen, it is making C double bond O. Now there will be negative charge over carbon. This is attacking this carbonyl carbon of the aromatic aldehyde. There will be negative charge generation. Okay, that is O minus. So see, there is O minus. Now ARCHO, this part is written in the left hand side. Now another carbonyl, that is COCH2 group, is also present. This O minus, it can attack here. Negative charge over oxygen. So as if it is intermolecular acyl transfer. Now why we are saying so? Because this is acyl group CH3CO. So now this acyl group, it is present here. But after this step, now it will be attached to the oxygen of ARCH. So see how it is happening. There is O minus, 6-membered ring formation. Now this O minus, if it is again making C double bond O, now there will be this OC bond will be broken. So OCOCH3, now it is attached here. It is COCH3, now it is present to this side, left hand side. Now we have taken another molecule of acetic anhydride. The negative charge, it is attacking this at this carbon. And again there is, this is intermolecular acyl transfer, that is within the same molecule. And this is also acyl transfer, because here this CH3CO, it is now attached to this ring. Finally, this H and this COCH3 group will be removed. You are getting CC double bond. So this is E2 elimination, because OCOCH3 group and H, these two groups are removed simultaneously. So this is E2 elimination. And we are getting this type of structure, but this is not final step. If OAC minus, which is already present in the medium, attacking here, there is negative charge. So see, this is the carbon where OAC, it has attacked. This negative charge, if it is further making C double bond O, this carbon oxygen bond will be broken, there will be negative charge. So ultimately there is removal of AC2O. So removal of AC2O, how it is getting, we are getting it, OAC, then there will be COCH3. So CH3CO OAC, that means CH3CO OCOCH3, which is nothing but AC2. If ACO is CH3COO minus, that means AC2O is nothing but this molecule, acetic anhydride. Finally, it will take proton from acidic workup if you are treating it with acetic acid, and we are getting alpha beta unsaturated carboxylic acid, which is Parkin reaction product. So remember, if you have used simple benzaldehyde and acetic anhydride, you are getting cinnamic acid. But if you are using any other reaction partner combination, suppose instead of CH3CO OCOCH3 you have taken ET group in place of CH3, then you are getting another type of molecule. But that is also cinnamic acid type of molecule. That is why we are saying you are getting final product in general for Parkin reaction is cinnamic acid derivative. Cinnamic acid is you obtain only when you have used PaCHO and acetic anhydride. In all other cases, it will be cinnamic acid derivative. So some more problems we'll discuss, and also number 6 reaction, and there is also some other reaction under miscellaneous. It is not complete yet, but today we have seen Parkin up to Parkin, which is number 5. So 5 reactions under miscellaneous reactions for aldehyde and ketones we have discussed. So thank you for listening. We are at the end of the session. We end here.